Hello, I'm Jan Koslevich. I'm coming from the University of Ljubljana, and we are starting a hands-on tutorial on open source research in structural dynamics and image-based experimental model analysis. With this, I'm starting to share my screen. The full source of the tutorial is available at this GitHub repository. So do check it out if you would like to know more details. And yes, let's start with this tutorial on this year's virtual IMAC conference. The tutorial was prepared with Domen Guryup and Clement Zaletel. The table of contents is shown here. So first we will look into some of the reasons why we need open source. Then we will go into some tools that we are typically using in structured dynamics. And finally, in section 4, we will go into high-speed camera measurements in structured dynamics. And in 5, real-life example of image-based vibration measurements. Okay. Let's start. Why do we need open source? Open source helps us avoiding to reinvent the wheel again. You know, we frequently have to code the same methods, and why waste that time? You know, if we would have the methods publicly available and everybody could contribute to those methods, then I think we would be able to put our time into other scientific ideas and not reinventing the wheel again. So this is the first reason. The other is fully reproducible science. You know, if we have the complete code exposed, then it is much easier to reproduce the scientific significance we are publishing in our papers. So this is the second reason. The third reason is faster science. You know, if we have the methods publicly available, then they are much easier to reuse. And yeah, other researchers can build on those methods. Here I'm showing some of the statistics. You know, when we make the particular package publicly available, there was quite a lot of interest between our peers, and we are happy about this. The second reason is that we all have the possibility to contribute, that usually the development is open. For example, the NumPy package, which is the basic library for array computing, has more than or close to 1,000 contributors, and it is used by approximately 400,000 packages. So 400,000 other packages are using this library, and the number of people that are downloading this package by year is huge. I know the number for SciPy package, which is the central library for scientific computing. It is estimated that roughly between 20 to 30 million people download this package each year. And this package is included in close to 200,000 other packages. And it is based on approximately 900 contributors. Okay. And why Python? Why Python? This is the next question. So we have seen in last years, we have here the last 5 years, we see that Python, the blue color, is steadily increasing in interest. While other programming languages see a decrease, for example, Java is slowly decreasing, also MATLAB and C are slowly decreasing. So why is Python becoming so popular? And as we see here, it is consistently rated among the top 5 most popular programming languages. So IEEE Spectrum list, in the last 3 years, the Python was selected as the #1 programming language. Here are 6 reasons, as seen by Kyla Matthews. So Python has a healthy, active, and supportive community. That is very important. You know, supportive community. That is one of the reasons why lots of people come to Python and stay with Python. Python has some great corporate sponsors. Here we are talking about Google, we are talking about Microsoft and other big companies. Python has big data. Python has amazing libraries, is reliable and efficient, and is accessible. The next reason is open source. You know, since 2001, Python is completely free for any use, including commercial. And this free should not be understood as free beer, but free as a bird. You can do anything with those tools. And usually, you know, most of the packages developed in the Python community are free for any use, commercial, non-commercial use, any. So the licenses in Python packages are usually very open and and free. Simple syntax, next reason. Finally here, huge and including and growing ecosystem. You know, PyPy has a collection of has a huge collection of Python packages. Currently, close to 280,000 projects are published here. And whatever you're working on, there is a big chance that a package is already available close to your interest. For example, we can check vibration fatigue, you know, and we will not find one package, but several packages which are related to vibration fatigue. And whatever your interest is, I'm quite sure that you will find something close to this interest. Okay, why structure dynamics in Python? So why we are preparing this tutorial for the community in structured dynamics? So I will try to explain. So we have the basic Python. The basic Python, you know, is the programming language used very broadly, but by people which are developing web pages, which are in scientific computing and other communities. So Python is very well structured. We have this core programming language. Then we have some basic packages like NumPy, SciPy, SymPy here for symbolic computing, let's say MicroPython for microcontrollers and other packages. So those are the core packages which make Python better and faster for particular tasks. Then we have the other ring of packages which are more task specific, like scikit-learn for machine learning, or here some packages for finite element analysis and scientific visualization. PowerView, VTK are supported in Python. And now here with the scientific community packages, so AstroPy is for the astrological community, BioPython is another community package, and other packages here. What we are looking for is a package or a collection of packages for the structured dynamics community. And in this tutorial, we will touch some of the packages which we are developing in laboratory for dynamics of machines and structures, like PyFRF for frequency response function, or PyEMA for experimental model analysis. What is our goal with those packages? I will try to explain that with the 7 stages of open source software as seen by Matthew Rocklin. So the first stage is, you know, just to make your source code public. Then the second stage is license for reuse. So you have to have an open and free license. You know, it should be free to do, so people should be free to do whatever they want to do with that package. You have to accept contributions. The development should be open, the decision making should be open. You should have multi-institution engagement and retirement. This also means that multi-institution, the governance should be multi-institutionalized, etc., etc. So the packages that we will show you in this tutorial are currently somewhere between 4 and 5, but our goal is to go to 6 and 7, and I'm inviting you to join us with this effort. And with this, I'm giving the word to Domen.
Hello, everyone tuning in. My name is Domen Guriup, and I will talk about some of the open source packages in the Python programming language that you might find useful if you're working in the field of structural dynamics. So the first thing you need to follow our tutorial is, of course, the Python programming language itself. And we recommend installing it by using the Anaconda distribution of Python, which is a scientific distribution that comes with a lot of the libraries, the core libraries that you will be using already installed. After that, you can install some of the additional packages that we are using throughout this tutorial. So these are the additional packages that you can install individually by running the commands listed here, or you can install all of the requirements after you've cloned or downloaded the code from our GitHub repository by running this command. So let's now import all of the packages and functions that we might need during this presentation. And I would like to start by telling you a bit about the SciPy project, which isn't just a library, but it's actually a collection of 6 libraries used in scientific computing. And I will talk a bit about those that are most useful if we're working in structural dynamics. So the first one would be NumPy. NumPy is at the core of all the scientific packages in Python, and it gives us the NumPy array object that we usually use to represent vectors and matrices in Python. So this is the core of the NumPy's functionality. Of course, it also gives us some basic numerical functions that we can use to do some data manipulation, linear algebra, and the Fourier transform, for example, and we will see all this in the examples that follow. So first, let's import the NumPy library again. Here is just a short example of how we usually represent vectors or arrays, as they are called in NumPy, in Python. So first we define a Python list, and then we use the NumPy array function to convert this list into a vector, a NumPy array. We can immediately note the difference between how these two objects now behave. So the Python list does not behave at all like we would expect a vector to behave, but the NumPy arrays, their behavior is as expected, so we can use them for numerical computing and computing with vectors. In NumPy, there's some useful functions. For example, the arrange function will create just a range of numbers from 0 to not including 10, with a step of 2 in this case. We can create with the linspace function linearly spaced values, so an array of linearly spaced values, and MATLAB users will be immediately familiar with this. And of course, we can also represent multi-dimensional arrays, which are matrices. So here's an example with a random matrix, but we can also, for example, manually create matrices by just inputting multi-dimensional lists into NumPy array, into the NumPy array function. In this case, you can see that we have some integer values and some floating point values in this example, and the NumPy array function automatically converts or selects the most appropriate data type for our to represent our values, which is the 64-bit floating point data type in this example. There's of course a lot more to NumPy, but these are just the basic things that you gain when using Python when using NumPy in the Python programming language. Another useful library is the matplotlib library, which is used for plotting with scientific applications in mind. It's used for data visualizations, and it was originally based on the MATLAB plotting library, so it has a familiar interface for those that are familiar with matplotlib. This is how we usually import it. So we import its pyplot module as PLT, which gives us a nice shortcut to using all of the functions. And if we prepare some data and then plot it using the plt.plot functions that are the usual and basic way to plot univariate functions in matplotlib, we can then easily create a legend with the selected labels, label our axis, or title the plot, include a grid, and this is what we get. The plt.show in this case is not necessary if we're using the Jupyter Notebook environment, but is necessary if you're just programming in the .py Python script. So plt.show is necessary if you're using other programming environments to run Python. The next thing that I would like to talk about is the actual SciPy library. So as I said, SciPy is a collection of six packages, but there is the SciPy library that includes code for some compared to NumPy more advanced numerical routines that can be used for things like signal processing, numerical integration, optimization, interpolation, and so on. And we will see some examples of what you can do readily with functions that are available in the SciPy library if you're just starting with Python. So for example, if we take our data set that we prepared above, the discrete points, and we're trying to interpolate the data, there's multiple ways to do it. But one of them is to use spline interpolation. So we import the appropriate class from the SciPy interpolate module. We prepare some values for interpolation, input our data created above into the interpolated univariate spline function that we've imported above, and what we get is a spline object that we can use to just compute the values in the intermediate points that we prepared above. So this is the result of the interpolation. Can be useful. So another thing that will be useful, maybe more useful for us, is the fast Fourier transform. And you can get fast Fourier transform in both the SciPy and NumPy libraries. So these are two examples for the two data sets that we've created above. One is using the FFT function from the NumPy library, and the other one is doing an FFT of the real values data set, and it's using the functions that we imported from SciPy. This is just for data for the normalization, and we also can prepare easily a vector of the frequency vector to plot the data, and this is what we get. So if we looked at the data sets above, we would see that we've created two sine signals, one at 2 Hertz and the other at 3 Hertz, both with an amplitude of 1, and this is exactly what we get as a result of our FFT. Now to maybe go into more specific, domain-specific libraries, PyFRF is one of them. It's been developed in LaDisk, and it's an open source package that can be used to compute frequency response functions from time series measured in an experiment, for example. We will start by importing it, and then we can define and read a data set. In this case, we're using another library that's LVM read that can read files saved by the National Instruments LabVIEW program. So we're just loading some acceleration measurements. From these measurements, we will select and read two sets of data. So we measured acceleration, and we've also measured force at the same discrete values of time. From the time delta data that we've also read from the LVM file, we can now calculate the sampling frequency, and we will use all this in our FRF estimations. So we can now go straight into the FRF library. We use its FRF class, input the data that we've read above, and we can start working on our FRF. We have a way of specifying what type of data was measured. So we've measured acceleration. We don't want any windows on our data in this example. And then we can, from our FRF object that we've created, get first our frequency axis and then our actual FRF, and we'll be using the H1 estimator to do this. Now we can use the matplotlib library and plot what we've computed, and this is the result of our computation above. Of course, we can use PyFRF to also compute different types of FRFs. So we can transform our FRF to accelerance, mobility, or receptance, and these are the results plotted in this example. PyFRF can also be used for spectral averaging. If we've repeated our experiment, let's say we have an impact excitation, and we've repeated it multiple times. So we have one of the segments, and we will begin by just loading the single segment in our FRF object. But then we will sequentially add data. So for example, you can use this workflow if you're during your experiment trying to evaluate the FRFs in real time. So each time we measure another set of data, we add it to our FRF object and then get the frequency axis and our FRF at the end. So this is the result of the averaged data set. Another useful library, another useful package is the PyEME library. If you've downloaded or visited our GitHub repository, you can get the links to all of these packages that I'm talking about in the template, but I'm sure you can also easily find them by just doing a simple web search. So the PyEME package is another one that I would like to talk about. It's a package used for experimental model analysis in the Python programming environment. More specifically, it's used for identification of model parameters from our measurements. So we'll be using our FRF measurements and we'll be doing some model identification. But first, we'll just be loading some additional data which has some more FRFs already measured and prepared. This time we're using the NumPy's binary data format. So we're selecting a single response, so a single column of our FRF matrix, and these are the FRFs that we have prepared in advance. On this data, we'll be doing model identification. So we're creating a new PyEME object called ACC because these are This is data acquired by using an accelerometer or multiple accelerometers. In this case, we can supply our FRFs that could be computed using the PyFRF module, of course, our frequency vector, and we can also limit our analysis to a specific frequency range, and we can also select our so the model order for our least squares complex frequency model estimator that's running in the background. We can now run the computation to get our system's complex poles and then plot our stabilization chart. Excuse me. So we have a stabilization chart that we can use to select the appropriate peaks, and you can see that we are also plotting reconstruction of our FRFs in real time to do some on-the-fly validation of our stabilization. Using the identified values, we can reconstruct FRFs. So the actual poles that we've selected during stabilization are now saved in the EMA object, the ACC object that we have here, and we will use it to get model constants. This uses the least squares frequency domain method to get model constants. We can also plot our model data, so our natural frequencies and damping ratios that we've identified during stabilization, and we get a matrix of model constants in the A attribute of our EME object. We also have a function that gives us normal modes, so we perform some normalization of the identified modes, and we'll just be plotting the first 3 modes, and we can see here in this example that these maybe remind us of bending modes of a simple beam, and this is the structure that we've actually measured in this experiment, so this is what we're getting. We can also use PyME to perform some additional analysis of our data. So for example, we can compute the AutoMAC matrix of our measurement. We can plot it using Matplotlib's IMShow function, and we can see it here. It shows us that maybe to identify the higher mode shapes, we would need some better spatial resolution of our measurement. And of course, we can also plot the reconstructed FRFs that we've computed above. So this is another way to validate our measurement and the identification process. So another package that I would like to talk about is the PyEDI package, an open source package meant for image-based displacement identification in Python. It currently implements the 2 algorithms that we most often use for this purpose, and these are the simplified optical flow method, which is a numerically efficient algorithm that can give us fast results appropriate to measure vibrations and do experimental model analysis with image-based data. And of course, we also have implemented a digital image correlation algorithm based on the Lucas-Canade method. For now, the package supports the Photrons MRAW file format. So this is the kind of data that we can use it on and load, but the package itself could be easily extended to other data formats. If you want, you can, for example, propose a pull request, and we can work together on additional functionality of the package. So in this basic example, we will first define the path, the relative path to our image files. We will create a video object that we will use for the analysis. We can now plot the first image example or any image in our that's been acquired. For example, the 100 image looks like that, and we can see a model hammer just hitting maybe in this instance. And to perform our analysis, first, of course, we need to pick or select the points for displacement identification. In this case, we'll just manually select 2 points. So they are both at the 25th row of our beam, and there are 2 different points. One is at the 100th column, and the other is at the 200th column in our image. These will be the 2 points that we will be analyzing. We will select the points by setting them into our video object. And now we will select also the method to use. SOF is the simplified optical flow method that I've talked a bit about above. We can do some additional configuration of our analysis, but in this case, we'll just use the default values that you can see here in the documentation. And then we will compute the displacements. So the method is numerically efficient. In 5 seconds, more or less, we've computed displacements for 2 points at 3,750 images. So we got our results. We saved them in the displacement variable. This is the shape. So we have 2 points, 3,750 images, and we have 2 directions, the Y and X directions. And in this case, we'll, for the first point, be plotting just the Y direction, which is also the direction where most of our displacements are happening in our video. With this, I will conclude the first part of our presentation of the open source packages in the structural dynamics field. And I will give the word back to Janko.
Hello, welcome back. So it's again my turn. And now we are with the package FLive. FLive is used for fatigue life estimation in spectral domain. First, I will prepare here a random excitation signal. This is just a random, just arbitrary random. And the fatigue life package has also, so first we need to prepare the spectral data. In this spectral data, we have all the spectral moments that we need later in the fatigue estimation phase. So we prepare this object SD, and with this SD object, we can also estimate the damage using the rainflow algorithm. This is obviously in the time domain, but as rainflow is usually the reference method, we prepare it. We will show also how to obtain the fatigue life with the rainflow method. It is very simple. We just needed to add the fatigue parameters and then call getLife method on the rainflow object, and we get the fatigue life of 235 seconds. If you would like to use the dirlik method, it is, very simple. We just need to send the spectral data to the dirlik method, and again on the dirlik object call the getLife method and add the fatigue parameters, and we get the estimation of 128 seconds. And if we would use the TIOBE method, it would be 146 seconds. There are other methods available which are listed here. Maybe one note, I'm not now comparing here the accuracy of the method. This is just pure random data. I will not go into details. There are research papers which deal with the accuracy of the rainflow versus other methods. And the FLive method is actually the algorithm which we used in our paper. So if you're interested in this, please check out those papers or write me an email if you cannot figure out which papers I have in mind. Okay, the next package is PyXC, so Python excitation signal as used in structural dynamics and vibration fatigue. We have supported the regular structural dynamics excitation signals like pulse, burst random, and sine sweep. In pulse, we are impulse, we are here relying on the SciPy windows. So we have supported close to 20 windows, including for sure the half sine excitation impulse. But then we also have support for random, and random defined by power spectral density. This is especially important because we can generate a stationary Gaussian signal, a stationary non-Gaussian signal, and a non-stationary non-Gaussian random signal. Okay, I will show here the last one. So non-stationary non-Gaussian signal. First, we have to define the power spectral density of the Gaussian excitation signal, which is shown here in this figure. Then we check, so that is now Gaussian, if the kurtosis is close to 3, and we see yes, it is, so this is Gaussian. Then we go on and prepare a stationary non-Gaussian signal with the same PSD as above, but we have a target kurtosis of 10, and yes, we obtain roughly 10.7. Then we have to add the modulation to that stationary non-Gaussian signal, and in the PyXC we have supported two modulation types. The one is defined with PSD, the other one is defined with cubic spline interpolation, where the nodes are based on beta distribution. The latter one performs better, and I will show it here. So we have to call the non-stationary signal and define the type of modulation, which is shown here. And then at the end, we get a kurtosis of roughly 9. And let's see how those signals look like in time domain. So in time domain, we have here the Gaussian signal, which has kurtosis 3, and here the non-Gaussian, non-stationary, based on beta distribution. It is obviously non-stationary, and the kurtosis is, as we shown here, 9. The power spectral density, and look at the power spectral density, both signals have the same power spectral density, as it is clear from this figure. Okay, if you're interested into details, please check out the showcase IPython notebook on the repository where the source code of PyXC is published. PyUFF, so Python Universal File Format package, is for reading and writing of UFF data sets. Which data sets are supported? We have listed here the most typical and usually used data sets, like for the coordinated system, for lines, for frequency response function, and 58 is the one that I will show here. So we have here, we can prepare example data set by calling the prepare method on the package PyUFF. And we have here which prepare methods we have. So for 15 dataset, 151, etc. So I will show you here for the 58 dataset. We have 3 points, and each of those points has a frequency response function. For sure, we have here the metadata, like a response node, response direction, reference direction or reference node, etc. And if we look on so if we try to show one of those frequency response functions, we see here the first 10 data points in the frequency domain as plotted here. Okay, if we would like to save that data to a UFF file, we just have to open a file. Let's say we have here the file name data temp 58 UFF, and then we just add this data set as it is shown here. If this was really fast, if you're interested in more, again, check out the showcase example at the source repository. Thank Thank you. And with this, I'm giving the word back to Clement.
Hello, my name is Clemens Aletel. I'm a PhD student at Faculty of Mechanical Engineering, University of Ljubljana, and I will be presenting the next part of the tutorial. So if we go to the tutorial itself, so I'll be presenting some details with respect to high-speed camera measurements in structural dynamics. And for purposes of this presentation, for this tutorial, we have prepared a measurement with a simple beam that is shown here. And we excited this beam using a modal hammer. We measured one acceleration here, and we measured, of course, the response with the high-speed camera. You can see that the beam is supported by foam pads to sort of simulate the free boundary condition. Now, this was the excitation of the beam. The measurement of the force, of course, also happened here in the modal hammer. To use this measurement, we have to first define the paths to the camera measurement and to the LVM file, so the force and accelerometer measurement, and this is done in this. And now we are going to load the video that we used, that we just recorded, So the video will be loaded using the PyIDI package that the one presented earlier. So pyidi.pyidi, and just input the file name or the destination of the video file. We can do this right now. Okay, so the images are now stored in the mRaw attribute, and we can check out the images anytime we want. So for example, 175th image here is shown with this code. So video.mraw and the image index, and then we will get this image, this frame. We can see this is what camera sees. It is worth mentioning here that the video that we presented here, that is shared online on GitHub, is made specifically to be shared on GitHub. The acquisition parameters are not selected as such to obtain the best possible results. The frame rate is too low. The resolution is not as high as it could be. So you must keep that in mind. So, but this is the video. We can see the hammer hitting the beam, and this is the first 1000 frames of the video. Okay, so the acquisition parameters that we mentioned just now are all stored in video.info dictionary. So we can check the frame rate. The frame rate is 15,000 hertz. Usually with high-speed camera, we would go 50,000 or 100 or 200, even 300,000 hertz for this kind of measurement. And then we will get better results. The shutter speed is also stored here. Image width, so 640 pixels, and image height 40 pixels is the height of the image that we recorded. Now, some important details regarding the setup of the measurement will follow. So the first thing is lighting. Lighting is pretty important, of course, because we are using the high-speed camera. And to obtain the best possible lighting, we usually use a histogram to check out how the lighting conditions are. An example is shown here. So this below is a histogram of this smaller red rectangle. And we can see that some pixels have a low intensity, some pixels have a high intensity, some pixels are in the middle. The optimum histogram is sort of encompasses the entire range of measurement range. So it's from the lowest intensity to the highest intensity. We will see how this can be a problem, how this is an error if the case is not such. Another detail is surface preparation. Of course, to use the gradient-based methods in order to identify displacements. A sufficient gradient must be present on the image or on the surface of the structure. And we need to prepare the surface to obtain that gradient. Now, to generate the stripe pattern or the random speckle pattern, a speckle pattern Python module can be used. It's available here on this link. In our case, we used horizontal stripes. And to compute the gradient of our image, we can simply use numpy.gradient and input a frame. And this gradient function will return the gradient in vertical direction and in horizontal direction. And we can check this out on this plot here. So we can see that one of the frames, the cross section, and along this cross section, we can see the grayscale values. These are in red. These are the grayscale values across this section. And then the derivative of this is the blue line. So this is the gradient, vertical gradient. And you can see that the gradient is significant, and we can use that to identify displacements because we prepared the surface of the beam. Now, some possible errors can occur when setting up the high-speed camera measurement for vibration measurement. And one of them is the focus. If the image is out of focus, especially if it's out of focus on one side and in focus on the other side, this can introduce significant measurement errors in the identification process. Here we can see that this part is out of focus, this part is in focus. This was due to because the beam was not perpendicular to the camera axis, and of course the out of focus error occurs. Another error that is common is the improper lighting. The lighting is, of course, very important, and it is hard to achieve, sometimes hard to achieve the uniform lighting of the entire structure. Here we can see that this side of the beam is very dark. If we take a look at the histogram of this side of the beam, so of this rectangular part, we can see that all the grayscale values are on the lower side. So this on the higher side of this of the histogram, there are no pixels. No pixels have a high intensity. The situation is reversed on the other side of the beam. We can see here that all of the pixels have the pixels have very high gradient value intensity values, and this is also not good. The image is saturated in this part, and information, of course, is lost because this is the highest value that we can record. Okay, so, and we want to sort of like, for example, yeah, we would like to have something like this, or maybe like this to, yeah, something like this to have an even distribution through the entire measurement range. Now I will present the real-life example of image-based vibration measurement, how to take a video that was just recorded and how to extract the model parameters. Okay, so of course, the first step is to identify the displacements from the video that we just recorded. We will be using the video that we loaded above. So that video has a lot of information in it. So in the info dictionary, there's a lot of information, and we will comment that out. And the first thing that we have to do is select the points on the frames or in the video that we want to identify displacements for. In this case, we will distribute the points evenly along the length of the beam, and the height of the points will be at the middle of the height. So with this code, we will generate some points. You can see that this is Y coordinate, this is X coordinate, and all the Y coordinates are equal, and the X coordinate is equally distributed along the length of the beam. And these points are now inserted or set for the video object. So we will configure the analysis now, and we will say video.setPoints, and we will input the points. Another thing that we have to do is set the method of computation. Doman showed you earlier the simplified optical flow measurement or the identification method. And here we are going to use Lucas Canade measurement, we will set the region of interest size, the maximum number of iterations, and interpolation order. Like so, and we can now show the points that we selected. We can see that all the points are equally distributed along the length of the beam. Now, the next part is to compute the displacements. The displacements could be computed, are computed using the video.getDisplacements. And this allows for multi-processing, so we can use as many processes as we want. For example, here I would use 4 processes for a course. But this, even with 4 cores, that would take sort of more than a minute, and we won't wait for that. We have here this factor that we multiply the displacements by. This is the size of a pixel, so we convert the displacements from pixels to meters. Okay, so and at the end we will get the displacements. We won't be running this code. We will just load the pre-computed displacements, and these displacements that we're going to load were computed exactly with this code. So we will get the same sort of result. And we can take a look at these displacements at location 0. So for this first point, we can see we get this. These are displacements in vertical direction, so in the y direction. Of course, we will only be looking at the vertical direction since our force was applied in the vertical direction. Now the next step is to compute the FRFs. And for the FRF computation, we first need some data. So number of frames, delta t, the duration of the measurement is computed here. And we will be limiting ourselves to the 4000 Hertz. Okay, so all the measurements will be cut off at 4000 Hertz. So this is the FRF limit. And we can use the NumPy FFT module to transform the time domain data into frequency domain data. This is this, and then we can also compute the frequency vector. This is this first line. And of course, as I said, we will cut off the frequencies above 4000 Hertz, and this is done in these 2 lines. Now, to compute the FRF, of course, we need also the excitation data, so the force measurement. The force measurement is contained in the LVM file name, so from the LabVIEW measurement file, and we will load that and extract the force measurement. The force measurement lasted for 1 second, but the video was 1/4 of a second, so we will only take the first 1/4 of the force measurement. The delta t is this, the FFT is computed, and then of course the upper frequency limit is applied. Because only 1 measurement was taken and no averaging was used, we can simply divide the FFTs and obtain the frequency response function. And we can take a look at the frequency response function. We can see that the first 2 modes are nicely visible, while from then on it's mostly noise. Okay, so now we have the frequency response function, and the next job is to perform the model analysis. Now, in this first part, we're just gonna use the camera data in the model analysis, and we're going to use the PyEMA package that Doman presented earlier. So the first thing that we're gonna do is we are gonna call pyema.model, and we are going to create the object named cam. In this model function or class, we are going to input the FRFs that we just computed, the frequency vector that we just computed, the highest polynomial order for the least squares complex frequency domain method, and the upper limit of the frequency. This is the frequency limit that we chose earlier, and it is 4000 Hertz. So now this is defined, and we are going to now compute the poles of these polynomials according to least squares complex frequency method. So the poles are now computed, but there are a lot of poles, and some are stable, some are not, some are physical, some are not. And to select the stable and physical poles, we are going to now call the select poles method from the cam object, like so. Okay, so this is the stability chart, and from here we can simply select the stable poles, like this one is stable, this one is stable, and probably here somewhere this is sort of stable, even though we will see that the damping ratio is negative. So we can print the model data of these selected poles. We can see that the first two natural frequencies are okay, the first two damping ratios are okay, but the third one is negative. So this is probably not okay. Now we have selected the poles, but we have to also reconstruct our frequency response functions and get the model constants. This is done by cam.getConstants, and we are going to use we're going to compute the poles for all the frequency response functions for all indices. So we can run this. Okay, and we can check the reconstruction. We can see that the reconstruction is nicely follows our measured FRF. We can also take a look at the model constants. We can see the first three mode shapes here at different frequencies. Now and now we're going to use a different approach. We're going to use the hybrid method. The hybrid method was developed by Yao et al. And for further details, you can see the article that is referenced here. But the basic idea is to use the acceleration data to aid in identification process. So first we need to take a look at get the acceleration data. We get that from the LVM folder that we just that we got the force measurement from. So we can load this, and we are going to use the PyFRF module that Doman presented earlier to create the FRFs. And we are going to, again, limit ourselves to the 4000 Hertz upper frequency limit. Now, if we compare the acceleration measurement to the camera FRF, we can see that the acceleration measurement is a lot less noisy. And we can use that to compute the more reliable poles. Okay, and again, to do that, we're going to use pyema.modal. We are now going to input the frequency response functions from the accelerometer. We're going to define the maximum number of poles, the upper F limit, and again, compute the poles, select the stable poles. We can now see that a lot of more poles are stable. We can select these poles like this. And if we now print the model data, we can see that we now have 4 natural frequencies and all the damping ratios are positive. And because the poles, of course, were stable, we selected the positive damping ratios. And now comes the hybrid part of the method. So we will now create another object using the FRFs from the camera. So this is this part. And the reconstruction, we are not going to, again, compute the model, the poles, but we're just going to do the reconstruction, but we are going to use the poles that were selected on the accelerometer measurement. So how we do that? We call the get constants and whose poles equals to ACC. So this is the object that we created earlier. So if we do this, now we have the reconstructed poles that are based on the reconstructed constants that are based on the poles from the acceleration measurement. And we can see the reconstruction here. Now we were able to even identify this higher mode. And if we take a look at the model shapes, we can see that the first 3 model shapes were correctly identified. And even another model shape we were able to identify another model shape. Now, of course, the results, as we said, this is a somewhat worse quality video, but still, even with this worst quality video, we were able to get decent results for the model shapes. Thank you.
Okay, thank you very much for attending this tutorial. With this, we are at the end, and I would again like to touch those 7 stages of open source software. You know, we have to go to the 7th stage, and this requires that you join this effort, and we are inviting you to help us with this effort. We are going up those 7 stages. If you are interested in this, please do follow us on GitHub or Twitter or ResearchGate. Additionally, we are thinking about organizing a summer school. We are not sure if it will be virtual or physical, but and we are also not sure when it will be. Obviously, due to the coronavirus situation, we cannot really plan right now how the situation will be in a few months. But if you are interested in that summer school, please fill out the form which we have prepared, and we will keep you updated about you know, if we will organize the summer school or not. Thank you very much. And yes, if you have any further questions or comments, join the discussion session at the conference.